Hello there again. Here is an equilibrium problem. It's a nice introductory problem. Things are pretty straightforward. So here we have two students, Juan and Bettina. They're carrying a 60 kilogram crate on a 4 meter board that's shown in the picture here. The mass of the board is 10 kilograms. Since Juan likes reading cookbooks and Bettina does push-ups, they put the weight closer here to Bettina. We want to find the force in newtons that each one exerts on the board to carry the crate. Now the forces that are going on the board, we've got Bettina here is going to be pushing up on that. We'll call that FB. The weight of this crate is going to go down. We'll call that FC. The board is going to apply a force to itself, and that, for the purposes of torque, we can locate that force at its center of mass. We have to assume the board's uniform, doesn't say otherwise. So that would be somewhere over here, would be the force of the board. We'll make that lowercase b. And then Juan applies a force up. Now it's in equilibrium. There's no acceleration. Linear acceleration is 0. Angular acceleration is 0. So that tells us that the sum of the forces in the x direction adds up to 0. But we can tell from the diagram that there are no forces in the x direction. So that's not surprising. But the sum of the forces in the y direction also have to add to 0. So Juan and Bettina have to lift up the equivalent force to the weight of the board and the weight of the crate. But we also know that the sum of the torques on this system has to be 0. Now typically summing up the forces is the easiest way to do it. However, if we look, we're going to see that we do not know Bettina's nor Juan's force. So for the sum of the forces in the y direction, we have two unknowns. So that's going to be a little bit of a dead end at first. So we're going to have to resort to the sum of the torques. Torques has the advantage of being able to eliminate unknown forces. And that comes from careful selection of the position of the axis. Now this board is not rotating, but we have to pick an axis. So the question becomes what, or where rather, is the axis of an object that's not rotating? Well, it turns out it's anywhere you want it to be. Literally, it could be anywhere. However, you want to select it so that it eliminates an unknown. So it would be wise to either put it at Juan's hands or at Bettina's, since those are the two things we don't know, and we'd like to eliminate one of them. So I'm going to put my axis at Bettina, and I'm going to mark it with a little x right there and put a circle around it. So I'm going to do the sum of the torques. I'm going to use the sum of the torques equals 0, and again, because I have too many unknowns to use the forces, and I'm going to specify that my axis is at Bettina. So when I look at the forces I have, I'm going to have a positive torque, or look at the torques I have. I've got a positive torque due to the board. I've got a positive torque due to the crate. And I've got a counterclockwise or oppositely directed torque, negative torque, due to Juan. And those are the only three torques I have. They add to 0. So I'm going to make a note there that the torque from Bettina is 0. And that's because she is at the axis. F Bettina is at the axis, so that applies no torque. All right, so for the board here, I need the distance to the center of the board, the force that the center of the board exerts, the sine of the angle between those two. Going to add to that the distance, the radial distance to the crate, the force from the crate, the sine of the angle between those two, and then I'm going to subtract the distance to Juan, the force from Juan, and the sine, the angle between those two. That adds up to 0. Now we can see that these angles are all 90 degrees in this case. So these sines are all sine 90, which is all 1. So That's not always going to happen, but that happens here. So I'm going to substitute in my numbers, and I'm also going to move this torque of Juan to the other side of the equality sign. So the distance to the board, that's at the center, so that's 2 meters. The force of the board is going to be its mass times the force of gravity. The mass of the board is 10 kilograms, and the acceleration due to gravity, not the force of gravity, times the mass of the board times the acceleration due to gravity. And then the sine of 90 is 1. And I can add the distance to the crate is 1.5 times the force from the crate, that's 60 kilograms, times the acceleration due to gravity, 9.8, and again the 1 for the sine of 90. And that's going to equal the distance here to Juan, that's the full length of the board, that's 4 meters, the force of Juan.
May I have your attention, please?
Sorry about that interruption. And then where were we? Juan's force is 4 meters away. There's the force of Juan, and of course the sine of 90 is 1. So we've got everything we need to find the force from Juan here. Just got to multiply these things out, and we'll do that real quick for you, where you have 2 times 10 times 9.8 plus the quantity. And we get that Juan applies a force of 269.5 newtons is the force from Juan. We can see here that it's essentially 2 significant digits, actually 1 with the 4 meters, but we're going to stick with 2. So we're going to say 270 newtons is the force from Juan. Now the force for Bettina, we can do that whole thing and move the axis over there again. That's a lot of work. We've got to know all the radiuses and all the angles. It's now easiest to use that sum of the forces in the y direction. If we do the sum of the forces in the y equals 0, we'd see that the force from Juan up plus the force from Bettina up minus the force from the board because it's down and minus the force from the crate would be equal to 0. And we can find the force from Bettina, since that's going to equal the board plus the crate minus the force from Juan. So the board is 10 times 9.8. The crate is 60 times 9.8. And Juan's was 269.5. I'm carrying out the whole thing here. I'll round off appropriately at the end. And there we get 416.5 newtons, so that's going to be 420 newtons for the force from Bettina. And we kind of ran out of space there, sorry. And there you see the end result. Alright, so pretty straightforward problem. When you have multiple unknowns in a static situation, it is usually best to apply the sum of the torques to determine one of the unknowns by placing the axis at the other unknown. Simplest way is, of course, using sum of the forces. However, when you have too many unknowns, you resort to the sum of the torques. Hope that was helpful.